the next paper titled Efficient and Robust Pallet Detection Using RGB-D Sensors and Synthetic Data Augmentation by Son Jong-ho, Meng-Woo-hyun, Kim Young-soo, and Jung Min-kook from Navifra Corporation. Right, thank you.
Hi, thank you. My name is Woo-hyun Meng. I'll be the presenter today on behalf of my team. I'll start with the intro, followed by background and motivations of our project, and dataset pipeline and methods that we use, and the experimental results and conclusions. So, you guys probably never heard of what Navifra is. We are a robotics company that works on mobile robots, special for logistics automation. So we mostly work on mobile robots and mobile forklifts, autonomous forklifts. So in order to make the forklift autonomous, we do need, there are about 3 key points, which are pallet pose estimation, motion control, which is about navigation, and the safety. Our company already has motion control technology and of course the safety, and we wanted to focus on pallet pose estimation. For pallet pose estimation, the requirement of the precision is that the lateral error should be 3 centimeters and the rotational error should be 2 degrees, less than 2 degrees, in order to successfully do its test. And the first thing we had to do was to choose the sensor. So the first option was the RGB camera. It's cheap, but as you know, it's very sensitive to lightings and shadows and occlusions. The second option was using LiDAR. We all know that it's very accurate in-depth information, but it's very expensive, and especially in the field of logistics, there are a lot of stretch racks or stretch films. So there's obviously reflection, so that could not be the case for us. And the last option was the RGB-D camera, which has color information and it gives good enough depth balance. And we decided to use the RGB-D camera for our project, for our research. And so we decided to use the RGB-D camera, and now we wanted to use or integrate artificial intelligence for our test. And we all know that there's always data sparsity challenge. Collecting real data in the warehouse, it takes a long time, and also it's expensive. And manual labeling is always time consuming. And also there's limited SIN diversity. And overall, there's always high risk of overfitting. So we came up with a new data set pipeline. Why don't we use real data, synthetic data, and diffusion generated data? So the real data were the data that we collected using Intel RealSense D435 camera that was mounted on our forklift. And the synthetic data were the data that were rendered using NVIDIA Omniverse that has a variety of palette sizes, textures, and camera angles, and also the lighting. And lastly, the diffusion generated data. We used Stable Diffusion Excel model to generate the palette data. And overall, there were 20,000 images that were used in our pipeline. And as for the data augmentation, there were 2 steps of data set augmentation. One was the traditional or conventional image augmentation, which is just flipping, changing the lighting conditions or those easy tasks. And the second one was the diffusion-based augmentation. Basically change like background and textures of the palettes and also background and everything. The metric we used to evaluate our model was for the data was IS and FID. And there were 4 loss terms that we used in our network when training. The first one was the bounding box loss. And the second one was center offset loss, which calculates the error between the predicted offset from the bounding box to the actual pallet. And the corner offset loss, which sums the errors between predicted and true offsets for each corner point. And the structure loss, that evaluates how closely the volume of the reconstructed 3D convex hull matches the ideal or actual pallet volume. And we integrate all those four losses to make a new loss column, which I will describe in a couple minutes. So our network is based on YOLO V11. So its backbone and neck are identical. But the difference would be that we use P2 to P6 in the backbone, P2 layer to P6 layer in the backbone. Or I'm sorry, we pass the output of the P2 to P6 layer to the neck in order to make the model learn more information. And those information would be the size of the pallets or textures and so on. The original YOLO, we believe that original YOLO it uses P3 to P5 outputs. And after that, we pass the output of the neck to head, and we actually regress the offsets instead of directly estimating the pose. And then we combine 2D corner predictions for the predicted vertices with depth information that we obtained from the RGB-D depth camera, and reconstruct the pallet's 3D structure. And then we validate the structural consistency by comparing its volume with the convex hull volumes. And like I said before, we integrated 4 losses using uncertainty-based weights to automatically balance them during training, and then enhance multi-task stability. There's the loss total below. So as you see here, the figure in the center is the actual real data that we collected, and the images that are around it are actually generated data. This was done to test the occlusion scenarios. So we wanted to generate data that there are like products or boxes on the pallets, and we use this table, SPXL, to do it. And it does look like a real world data. And here's the actual test results. Those are not generated data, those are real data, or not. Those are real images that we took when we were testing. So as you see here, we were able to, the model was actually able to accurately estimate the pose, even under occlusion, even when there's like objects or products or the boxes on the pallets. So we tested our model, or trained our model, using only synthetic, and real plus synthetic, and lastly, our models, real, synthetic, and generated. And as you see here, the model showed the best performance when we trained with all three data. Also, offset regression achieved higher OKS than direct key-point estimation, which proves that offset-based methods are robust under even occlusions. Here's the video of our forklift actually doing autonomous walking, or actually taking the product. Thank you.
Okay, thank you very much. Any questions for the author? Presenter?